Hello, welcome back to Lecture2b of Quantum Computer Systems. In previous lectures, we talked about the first two of the four principles of quantum computation. We used the superposition rule to describe the state of a qubit, and we define the transformations on a qubit by unitary quantum gates. Today, we're going to finish the remaining two principles, namely quantum measurement and composite systems to describe multiple qubits. In today's lecture, we will also come across concepts like multi-qubit quantum gates, and we will revisit the entanglement properties and introduce a more general representation of quantum states called mixed states. Okay, today's lecture is going to be a bit technical, so we'll be using the notation we introduced from Lecture 2a. Let's take a quick recap of what we learned last time. Well, we learned that a qubit can be in a superposition quantum state, and in this cat notation, we write down as psi equals alpha times 0 plus beta times 1, where alpha and beta satisfied this normalization constraints, alpha squared plus beta squared equals 1. You can also write it down as a two-dimensional complex column vector, alpha and beta, like this. And we learned that there's a nice visualization of a qubit state on what we call a Bloch sphere. Essentially, you rewrite the quantum state in the spherical coordinates, and a quantum state corresponds to a point on the surface of the Bloch sphere. Great. So sometimes it's also convenient to have a notation for the adjoint of the state vector psi. We call that the bra notation. So the bra state psi is just the row vector where the element of the vector is the complex conjugate of the coefficients alpha and beta. Now, two more pieces of notation that we will be using very frequently today is the inner product and the outer product of quantum state. The inner product of quantum states is a bra state times a gas state, which can be shorthanded as psi1, psi2, making up to a bracket. This inner product of quantum state is a common measure of the overlap between two quantum states. As you can see, if the inner product of the same state gives you 1, and the inner product of two orthogonal states like 0 and 1 gives you 0. Next, the outer product is the gas state times the bra state. I like to write it as shorthand psi1, psi2, like this. Now, this is typically used in the context of projectors or operators, simply because if you multiply the outer product of 0 state on our original quantum state psi, you're going to be left with only the 0 component of the quantum state. In some sense, projecting the quantum state to the 0 basis will make it more rigorous in the next few slides. Next, we learned about how transformations on a qubit looks like. And in particular, it's a unitary transformation, where unitary means you can write down the transformation as a matrix that satisfies this, meaning its adjoint is the inverse of the matrix. And some common transformation that we will be using in this course are the following. We have polygates along three different axes, x, y, and z, and their matrices correspond to the Pauli matrices, x, y, and z, written down here. Two other common quantum gates are called the Hadamard gate and the phase gate. In particular, we'll be looking at the Hadamard transformation a lot in today's lecture. We also talked about a more general set of transformations corresponding to rotations of the Bloch sphere along different axes. And the rotation gauge matrices is defined as the matrix exponentials written down here. In the context of rotations, these poly XYZ gates are essentially rotations along different axes by 180 degree, which is pi radian. And this phase gate is essentially our Z rotation, about 90 degrees. We also learned from last lecture that we can represent arbitrary rotation about arbitrary axes as a composition or a sequence of Z and X rotations. In particular, we can think of arbitrary rotation as first a Z rotation with some angle, and followed by an X rotation, and finally another Z rotation. Great. So in today's lecture, we are going to learn the other two principles of quantum computation, namely what happens if we measure a qubit and how to represent a system with multiple qubits. So let's get started. So what happens if we measure a qubit? Well, let's use this simple quantum circuit to illustrate the measurement process. The first line of the quantum circuit is for initialization. Here we initialized a quantum register of size 1, so 1 qubit, and a classical register of size 1 also for storing the measurement outcome of the quantum register later. So after the initialization step, we have a qubit in quantum state 0. The second line of the quantum circuit is a Hadamard gate. Its unitary matrix representation is written here. So after the Hadamard gate, we have transformed the initial quantum state 0 to a linear combination of zeros and ones. Each have coefficients 1 over root 2. Now, where is the quantum state on the Bloch sphere after the Hadamard gate? Well, from what we know in the previous lecture, it sits on the surface of the Bloch sphere, representing the plus state. Okay, now the third line of the quantum circuit is a measurement. When we measure a qubit, we need to specify the basis that we measure in the qubit. And in this case, we are assuming it's measuring in the Z basis. The measurement basis specifies how we look at the information inside of a qubit. And to measure in the Z basis means we project the quantum state along the Z axis, which consists of the quantum state 0 at the North Pole and the state 1 at the South Pole. So with some probability, the quantum state will be projected to 0, and some other probability it will be projected to 1. So we say the measurement outcome could either be 0 or 1, and the probability of measuring 0 is the square of the coefficients on the basis 0. So 1/2. Similarly, we can derive the probability of measuring 1 to also be 1/2. One more thing that's sometimes of our interest is the post-measurement quantum state. And in this case, it's half probability 0 and half probability 1. So if you perform the same measurement on Z basis again, In the first case, it will always give you 0 every time, and in the bottom case, it will always be 1. And there's a more formal and mathematical way of writing down this measurement process. We can write down the measurement basis as a observable, and observable z for measuring the z basis is defined as a sum of orthogonal projectors. In our example, we have two projectors, one for 0, another one for 1. And the projector for 0 is E0. We can write them down as the outer product of the 0 state. And the projector for 1 is E1 equals the outer product of the state 1. So Z is the summation of E0 and E1 with coefficients A0 and A1. These A0 and A1s are the eigenvalues associated with the projectors. In our case, we have +1 for 0, -1 for 1. For this reason, sometimes we say the measurement outcome are the eigenvalues associated with the qubit state. Now, with this representation, the measurement probability calculation becomes very convenient. The matrix form for the E0 projector is 1, 0, 0, 0. And similarly, the matrix form for E1 is 0, 0, 0, 1. And if you have a quantum state psi, and in this case it's the plus state, the probability of measuring 0 can be conveniently written down as the inner product form psi E0 psi. And similarly for the probability of measuring 1, it's equal to psi E1 psi. And you can verify that they are equal to 1/2. Another concept that appears commonly is the expectation value of the observable. In our case, we denote it as bracket z, which is defined by summation of AI probability of measuring AI. And very conveniently, this is equal to psi z psi. So what is the expectation value of observable z for our circuit? Well, we have the plus state and the z observable, which is equal to +1 times half probability and -1 times another half probability. So the expectation value is 0. Now, another thing we care about is the post-measurement quantum state. When the measurement outcome is A sub I, or measuring I, then the quantum state becomes psi prime equals E sub I times psi, the input, over square root of psi E sub I psi inner product. Essentially, we have the projected state in the numerator and a normalization factor in the denominator. And in fact, this is a general formalism to describe orthogonal measurements, where we specify a set of orthogonal projectors E sub I that satisfy the following criteria. First, it's orthogonal, so EI times EJ is delta IJ EI, which means that EI squared is EI itself, and EI times EJ is 0 if I and J are different. And second, EI is Hermitian, so the adjoint is itself. And third, it's also complete. So the summation of over I e sub I is the identity. So now we can use this formalism to study orthogonal measurements along a different axis. Now, what if we measure in a different basis? This time we specify a new observable called x, which represent the projections onto other states, namely the plus state and the minus states. Again, I'm writing down the observable as a summation of the two projectors, E plus and E minus. Now assume we are still using the same quantum state psi equal to a plus state. We can quickly calculate the probability of measuring psi to be plus as psi e plus psi. Similarly, the probability of measurement outcome minus is psi e minus psi. If you expand this equation, you will get plus as the input state psi, and E psi is the outer product of plus and another psi, so this is 1. And similarly, you can get 0 for the probability of measurement outcome minus. And again, the expectation value of the observable x on our input state psi is psi x psi, which is equal to 1. In fact, there are two very nice ways to visualize a measurement in the x basis. The first one is a algebraic picture, and the second one is a geometric picture. So for the first algebraic picture, we can think of measurement in the x basis as rewriting the quantum state psi in a new basis. So psi equals some coefficients times plus some coefficients times minus. And the coefficients here, let's denote it as alpha plus and alpha minus, can be very conveniently calculated by this inner product. So the probability of measuring plus is just alpha plus squared, which is alpha plus times alpha plus, which is in agreement with our original equation. And similarly, for the probability of measuring minus can be calculated by alpha minus squared, which is equal to psi e minus psi. So now measuring a different basis is just rewriting the quantum state in that basis. We can calculate the coefficients for that basis with this formula. The second way to visualize this measurement in a different basis is a more geometric picture. You can think of it as first rotate the new measurement basis to be aligned with my good old z-axis, and then just perform the measurement in z-axis as we did before. So in this case, we can apply a rotation of the Bloch sphere so that my z-axis is rotated to align, the x-axis is rotated to align with the z-axis. And that transformation is the Hadamard gate. In other words, measure x is equivalent to Hadamard gate plus measure z. So far in the lecture, we have talked about system of a single qubit, together with quantum gates and measurement on a qubit. Well, let's now take a look at a system of multiple qubits. Then let's begin with something simple, a system of two qubits. Suppose Alice has a qubit in a quantum state psi A, and Bob has another qubit in a state psi B. What is the joint or composite system of A and B? Well, from the superposition rule, we know that it could be in a linear combination of 0, 0, 0, 1, 1, 0, and 1, 1. But Alice and Bob came in with qubits in particular quantum states with the coefficients alphas and betas. So what is the coefficients for this linear combination? The answer is called the tensor product. And let's now take a look at what is the tensor product of A and B. We take the quantum state psi A, we take the quantum state psi B, and the tensor product of the two is equal to a vector of size 4, and the four coefficients are alpha 0 times beta 0, alpha 0, beta 1, alpha 1, beta 0, alpha 1, beta 1. So these four coefficients correspond to the coefficients in front of the four basis states. More formally, we say the joint quantum state psi AB of two systems, psi A and psi B, is the tensor product, psi A tensor psi B. Now we know how to write down a system for multiple qubits. Let's take a look at the quantum programs for multiple qubits. In this example, again, the first line is initialization, and after this line, we have a system of two qubits in a quantum state psi AB equals 0, 0. Okay, so after the initialization, we have 0, 0. And then the second line is a quantum gate, Hadamard gate, on the 0th qubit. In fact, implicitly, we are applying a no-op or identity operation on the other qubits. So together, the unitary gate on the two qubits is Hadamard gate tensor the identity gate. So let's now take a look at what is the tensor product two gates. You can write down the Hadamard gate first, and it will be tensored with the identity. As a result, we have the 1 over root 2 factor on a 4 by 4 matrix. We break the Hadamard gate up into 4 blocks. Apply the identity. As a result, we have this 4 by 4 matrix. So the recipe for writing down the joint multi-qubit unitary gate from single qubit gates is again through tensor product. So after the Hadamard tensor I gate, our initial quantum state psi is transformed to 0, 0, and 1, 0 with coefficients 1 over root 2. You can check this by verifying the following equality. H tensor I on input state 0, 0 will produce 1 over root 2, 0, 0 plus 1, 0. Now the final line of the quantum circuit is a CX gate applied on both of the qubits. This is a conditional gate, or sometimes called controlled gate. So what does this controlled gate do? Suppose you have two qubits, A and B. Then the CS gate will do nothing if psi A is 0, and apply the X gate on B if psi A is 1. So let's take a look at our example here. In our example, A is the first qubit, B is the second. In this first case, A is 0, so the CX gate does nothing. In the second case, A is 1, so we apply X gate on the second qubit and it becomes 1, 1. In fact, we can just write down the other two cases, even though they are with coefficients 0. Let's see what it does on the other two bases. In this case, A is 0, so it does nothing to B. And finally, in this case, A is 1, so we flip it back to 0 for B. The coefficients for the four bases here again now is 1 over root 2 for the first one, and 1 over root 2 for the third one, and 0 everywhere else. So the final state, psi AB, after our controlled CX gate, is 1 over root 2, 0, 0, plus 1, 1. Notice that this is the entangled state. Notice that this is the entangled state. This is why sometimes conditionals or control gates are also called entangling gate. So things become very interesting if we perform a measurement on a subsystem of an entangled state, and that is called the partial measurement. For example, say Alice and Bob each holds on to one of the two entangled qubits, and suppose Bob suddenly wants to measure his qubit. What would happen to the state of Alice's qubit? Okay, so let's find out. Suppose we have two qubits, same pair of qubits we had in the previous slides. So up to this point, we have a joint quantum state psi equals 1 over root 2, 0, 0, plus 1, 1. And now Bob decides to measure. Now in the Feynman path diagram, we have coefficients 1 over root 2 on the 0, 0, and 1, 1 state, and 0 coefficients for the other two. So in this notation, the first qubit belongs to Alice, and the second qubit belongs to Bob. So the next step is to perform measurements for Bob, which is the second qubit in our quantum state. Just by reading off the measurement outcome from each of the possible states, Bob would measure 0 for the first case and 1 for the second case. And we know the probability for Bob to measure a 0 is the square of the coefficients on that path, which is 1 over root 2. So Bob will measure 0 with half probability. Similarly, another half probability for measuring 1. Let's take a look at the state of A after the measurement. We know for the first case, we have 0 for Alice. In the second case, we have 1 for Alice. So the first case is conditioned on Bob measuring 0. And the second case is conditioned on Bob measures 1. Where the measurement outcome of Bob is a probabilistic event. So the state of Alice states sounds like a statistical mixture of 0 and 1. In other words, Alice's quantum state is 0 with probability 1/2 and 1 with probability 1/2. If we locate these 2 points, namely 0 and 1. On the Bloch sphere, it sounds like we are a mixture of these two states, each with probability 1/2. Great. So now if Alice decides to measure her qubits, we know that in the first case, she will measure 0. In the second case, she will measure 1. In other words, if Alice measures her qubit immediately after Bob's measurement, she would get measurement outcome that is correlated with that of Bob. That is why we say the measurement outcome of entangled quantum state is correlated. Now, there is more to this entangled quantum state psi. It's not only correlated in the 0 and 1 basis, it's correlated in other bases as well. So let's take a look at that situation. What if Bob measures his qubit in the x basis? Well, from earlier, we know that it's equivalent to Bob performs a Hadamard transformation that rotates the x-basis to be aligned with the z-axis, and then perform a measurement along the z-basis. Now let's see what happened to Alice qubit in this case. Like before, we write down the quantum state, then Bob performs a Hadamard transformation, followed by a measurement in the z-basis. So let's see what happened. After the Hadamard transformation on the second qubit, we get 1 over root 2 of 0, 0, 1 over root 2 of 0, 1. And in the bottom case, 1 over root 2, 1, 0, negative 1 over root 2, 1, 1. So the overall coefficients for each of the 4 paths is calculated by multiplying all the coefficients along the path. Okay, now let's see what if we perform a measurement along z-axis for Bob. Bob will read out 0 in the first case, and 1 for the second, 0 for the third, and 1 for the fourth. Now remember, Bob measuring 0 and 1 in this case corresponds to him measuring plus and minus in the x basis. 0 means plus state, 1 means minus state. Let's quickly calculate what is the probability for Bob to measure plus. The probability for Bob to measure a plus state is the first case and the third case. So that corresponds to square of the coefficients and sum over all the possible outcomes, which is also 1/2. And the probability for Bob to measure in minus is the same thing with half probability. Okay, what is the state of Alice's qubit? In each of the cases, we can write down her qubit state corresponding to the first qubit. Notice that again, Alice's state is conditioned on the measurement outcome of Bob. So if Bob measures plus, which is the first case and the third case, which means if Bob measures plus, Alice has a state of 0 plus 1. And when we normalize her quantum state, we see that it is also the plus state. So again, this is if Bob is plus. Now if Bob measures minus state, then we have 0 minus 1 for her qubit. After the normalization, this is the minus state. Conditioned on Bob measures the minus state as well. Now it looks like for Alice, it's another statistical mixture, and this time it's a mixture of plus and minus. In other words, the state of A is plus with probability 1/2 and minus with probability 1/2. So the measurement outcome of Alice and Bob are correlated this time in the x basis as well. Now on the Bloch sphere, We know the state of Alice qubit is a mixture of the quantum state plus here and minus here, each with probability 1/2. Well, can Alice and Bob use this as a mean to communicate with each other? It feels like Bob can tell Alice the information about along which axis did he measure to Alice instantly, because the joint state of Alice and Bob collapsed immediately after Bob's measurement. And depending on the axis along which he measured, Alice would end up with either the mixture of 0 and 1 or a mixture of the plus and minus state. Furthermore, it looks like this process is independent of how far Alice and Bob are. They can be light years apart and still able to perform a measurement this way. Well, can they accomplish instant communication using entanglement? Well, not quite. In fact, there's no way for Alice to distinguish the mixture of 0 and 1 from the mixture of plus and minus solely from her measurement outcomes. Notice that if she measured her qubit in the z basis, in both cases, she'll always end up with a uniform distribution of 0 and 1. But there is something interesting about this entanglement because it looks like these measurement outcomes are correlated not only in the z basis, but also in the x basis. In fact, they are correlated in a infinite number of bases. And this led us to use a more complete representation of a quantum state called the mixed state, or a density matrix representation of the quantum state. Now I have drawn the two statistical mixtures of quantum state on the Bloch sphere. They correspond to the two scenarios, namely the state 0 with probability 1/2, state 1 with probability also 1/2, and also the plus state with probability 1/2, or minus state with probability 1/2. Now we have a better way to represent the statistical mixtures of the two scenarios called the density matrix. The density matrix of an ensemble or statistical mixture of quantum states is rho equals the summation of probability p sub k times the outer product of the quantum state psi sub k where the mixture is that with probability p sub k, you will have a quantum state psi sub k. Now let's take a look at the density matrix representation of the first scenario. So rho is equal to probability 1/2 times the outer product of 0 plus 1/2 times the outer product of 1, which is equal to 1/2 along the diagonal and 0 half diagonal. It's a 2 by 2 matrix. For the second case, we have rho equals 1/2 probability being the plus state and 1/2 probability in the minus state, which also gives you the same matrix. This is a very clean mathematical way to represent the state of Alice's qubit, which is independent of Bob's measurement outcome. In fact, if you look more closely, there are infinite number of ways to write down the same density matrix as a statistical mixture of quantum states. For example, I can find in the quantum state here with half probability and another quantum state the opposite side of the Bloch sphere with another half probability. So there are infinite number of ways to expand the density matrix into a mixture. And these mixtures are all related by sort of rotation of the Bloch sphere. In other words, these mixture expansion is related by unitary transformation. And more rigorously, I can write down this equation. Rho equals summation of I p sub I psi I outer product to represent one way to write down the mixture. And another mixture summation over j, qj, times the outer product of phi j. If they're equal, then we know they're related by unitary transformation. Means that all the square root of pi psi i's, or different I, written down as a vector, is related by some unitary matrix times the vector by all the qj's and phi j's. And in general, this is true for multi-qubit quantum systems as well. Okay, so that wraps up our introduction to the basics of quantum computation. And from next lecture, we will be talking about the architectural aspects of quantum computing, and in particular, how do we use the properties that we learned to perform computation in a scalable and efficient way. See you next time.